In the world of geotechnical engineering, we often treat the ground beneath our feet as a uniform, predictable block. But as any site engineer will tell you, nature rarely works in monocultures. This is where the work of Harold M. Westergaard becomes essential. A brilliant Danish-born engineer who became a powerhouse at Harvard, Westergaard realized in the 1930s that the widely used Boussinesque theories didn't quite cut it when dealing with varved or stratified soils. Those distinct layers of silt, clay, and sand that look like a stack of pancakes under the earth. Bridging the gap in stratified soil. Westergaard's primary contribution was acknowledging anisotropy. While earlier models assumed soil was isotropic, having the same properties in every direction, Westergaard noted that layered soils are often reinforced by thin, stiff, horizontal strata. These layers act like a series of tiny internal membranes, resisting lateral expansion more than vertical compression. By introducing a model that accounted for these non-homogeneous conditions, he provided a more realistic way to calculate how stress actually travels through sedimentary deposits. A history born of necessity. The historical context of his research is tied to the massive infrastructure boom of the mid-20th century. During his time as a consultant for the Bureau of Reclamation and his work on the Hoover Dam, Westergaard saw firsthand how critical precise stress distribution was for massive concrete structures resting on complex foundations. His 1938 paper, A Problem of Elasticity for the Application of the Theory of Shells, laid the groundwork for what we now call the Westergaard analysis, bridging the gap between pure mathematics and practical mud-on-the-boots engineering. Breaking down the formula. When we look at the math, Westergaard's formula for a point load calculates the vertical stress, sigma sub z, at a specific depth and radial distance. To keep it practical for US-based projects, we use US customary units, measuring force in pounds, or kips, 1,000 pounds, and distances in feet. The formula introduces a specific Poisson's ratio effect, often simplified for many soil types. It is expressed as shown. In the specific Westergaard case where Poisson's ratio is assumed to be 0 for perfectly stratified material, the constant factors adjust to 1 over pi, and the denominator structure shifts slightly. Comparing the giants. Why choose Westergaard over Boussinesque? It comes down to the spread of the load. In Boussinesque's world, the stress fans out widely. In Westergaard's world, the world of stratified soil, the stress is more concentrated directly beneath the load because the stiff horizontal layers pinch the pressure, preventing it from dissipating sideways as easily. If you're building on soft clay with thin sand seams, using Westergaard isn't just a stylistic choice. It's a safety requirement to ensure you aren't underestimating the pressure on deeper layers. The modern application. Today, even with the advent of complex finite element software, Westergaard's influence remains a staple of foundation design. It serves as a vital sanity check for engineers working in coastal regions or glacial lake beds where stratification is the rule rather than the exception. By understanding the history and the mechanics behind this formula, we honor a legacy that turned the chaotic layers of the earth into a solvable, predictable science, ensuring our skyscrapers and bridges stay exactly where we put them.